Okay, Thomas and Alicia, can you hear me? Can you let me know if you can hear? Okay. All right, well, we're going to go ahead and get started. We're doing 3 sections. This week we're going to do sections 1.5, 1.8, and 2.16. And I'm actually going to start with section 1.8 first. And then I'll do the other 2 sections because they kind of go together on probability. So let's do 1.8 first, which talks about means. And so what's a mean? So a mean is an average. So if we have a set of data, and by the way, we're in a cycle now called cycle 1A, which is on probability and statistics. So we're starting a new section this week. So the mean, or the average, is a measure of the center of a data set. And we're going to talk about 2 other measures in a minute, but right now the mean, most students are familiar with it. So an example they give you right here is if Peyton Manning threw a football 85 times for 769 yards total, then his average per throw was take 769 and divide by 85, a little bit more than 9 yards per throw. So one example from your book, again, this is a nice review of material we covered before. Here's a bar graph. And so they're showing enrollments in community colleges in Chicago, and they want to know what's the average enrollment. So at the top of the bar, it tells you the actual enrollment. So in order to get the average, what do? We add those numbers together, 1, 2, 3, 4, 7, and then divide by 7. And when you do that on that example, you come out with an average. If you get the total is 100,313, and then divide by 7. And so we get an average of about 14,300 students per college. Okay, and then there's a little block in your book here on page 57 on how to find the mean. I think most students know how to do that. It's not too difficult. And one thing, if you want to think about, the mean is really like the balancing point of the data set. So it's the middle such that the numbers below it, the distance from that number to all the numbers below, equals the distance from that number to all the numbers above. So it's really the balancing point for the data set. So let's work an example. So 8 servers work at a restaurant and they earn the following tips on a particular night. If their practice is to evenly share the tips, how much would each server receive? So what are we going to do? We're going to add up those 8 numbers and divide by 8, and we get a little bit more than $88 on average each server would get. I think Alicia has a question, so I'm going to wait for a minute. The instructions will tell you how to round. All right, and the reason I rounded here to 2 decimal places is because it's money. But in your problems in my math lab, they'll always tell you how to round off. So it really depends on the application. But when we're talking about money, 2 decimal places makes sense because we're talking about money. Good question, though. Okay, another measure of the center of a data set, or the most common value in a data set, is called the median, and that's the value in the middle when we put the data in order. So if we go back to the tips example, if I put those data values in order from smallest to largest, and remember there were 8 in this data set. So when there's 8, the median is going to be, let me get my pen here, it's going to be the average of the middle 2. So 1, 2, 3, 4. So the median this time is going to be the average of the middle 2 data values because we have an even number. So in this case it's $80, and if I round that off it would be 10 cents. Now if there's an odd number in a data set, let me go back for a second. If the 145 hadn't been in there and had been 7 data values, then the median would be the middle value. So if we took this one off, we would go right to the middle, which would be the 72. So even number of data values, you average the middle 2. If there's an odd number, the median is the middle value. And then the third measure of center is called the mode, which is the most frequent value in a data set. So let's find the mode of this data set here. Sometimes it's helpful to put them in order. In this case, I can see that the only number that occurs more than one time is 43. So we say the mode here is 43. Now some data sets have no mode and some data sets have more than one mode. So every data set will have a mean and a median. It may or may not have a mode, and in fact it may have more than one mode depending on the data set. So mode is the most frequent. If all the data values appear once, then we say there is no mode because there's no most frequent value. They're all the same number of same frequencies. Okay, so that was means, which is pretty simple. I don't think anybody will have trouble with that section. Now, the next two sections are on probability. And the first section is 1.5, which is talking about frequencies, relative frequencies. How often does something occur? So for instance, if we have 15 women in a group of 75 diagnosed with cancer, then the relative frequency of getting cancer in that group is 15 out of 55, 1 out of 5, 0.2, or 20%. And a relative frequency can be written as a fraction, a decimal, or a percent. So fraction, you want to simplify it, so this really should be 1 out of 5. Decimal, or the percent, which means the decimal multiplied by 100. So let's try an example from your book. A national survey asked how many people were living in the respondent's household. The table below shows the results. Find the relative frequency of households with more than 8 people and interpret that. So now here we get into, when we get into probability and statistics, we get into interpreting the words carefully. So with more than would mean what? Oops, sorry, I didn't mean to go over there. I was trying to extend this line here. Does that include 8 or not include 8? So we have to think about what those words mean. So if it says more than, that means what? 8 or more. So what we're going to do is look at the categories with more than 8. I'm sorry, not 8 or more than 8. That's going to be this category plus this one plus this one. All right, and you also need to have the total in the table, which I don't think they gave you. So to get the total, you add up the numbers down here for the denominator. That's the total number of people that responded, 2538. And how many of those had more than 8 in their household? 3 plus 1 plus 1, 5 over 2538. And I think I also showed this as a percent, rounded off, I'm sorry, the decimal and a decimal, and then it would be, the percent would be 0.2%. All right. So approximately 2 out of every 1,000 had more than 8 people in their household. That was the interpretation of that particular question. All right, and then this section also talks about experimental probability. So probability is the likelihood of something happening. And when we talk about experimental, it means we have to actually gather the data. We have to use the relative frequencies to answer the questions. So things like surveys are experimental probability. So a recent survey showed 40% of Americans approve of the job the president is doing. So in other words, we can expect 40 out of every 100, or 4 out of 10, or 2 out of 5 to approve of the job the president is doing. You could interpret this as an experimental probability and say that if you randomly pick an American, you would expect that person who favors the president about 40% of the time, or there'd be a 40% chance that person would favor the job that, or approve of the job the president's doing. Here's an example from your book. They did a poll to understand coffee habits, and we want to fill in the table, and then we're going to ask some questions. So how do we fill in the table? So we gave that in each age group, we gave the number of people who said they drink at least 1 cup of coffee per day, and then we also gave the total. So in order to find the people who don't drink at least 1 cup, what are we going to do? We're going to take 744 and subtract 357, 519 and subtract 342, and so forth down the table. So when I do that, first I need the total here, and I also need the total over here, and then I'm going to subtract. So 744 minus 357 gives me 387. 519 minus 342 gives me 177. 266 minus 196 gives me 70. And then if I add those up, and then I have a nice check here because I can do this plus this and get a total of 1529, and I can also double check and make sure these add up to 1529. All right, so now let's answer some questions. Find the experimental probability that someone in each age category drinks at least 1 cup of coffee per day. Which age group had the highest probability? So let's go back to the table for a minute. At least 1 cup a day means we're going to take this and divide by the total within each age group. This divided by this, and this divided by this. So let's go ahead and do those calculations. So the first group is about 48%, the second group is about 66%, and the third group 74%. So if we want to interpret this, we say that the 65 plus group is the most likely to drink at least 1 cup of coffee per day. 74% of them do, about 3/4. And the youngest group is the least likely. So there's a little interpretation. And then one other question off of this table, actually 2 more. Find the experimental probability someone over 65 does not drink at least 1 cup. What's the fastest way to find this? Let's go back for a second. The probability of somebody 65 or older drinking at least 1 cup was 74%. So the probability that they don't drink at least 1 cup would be 1 minus that. So we can either take the number from the table who didn't drink at least 1 cup and divide by the total in that age group. Or we can take the other example, which is 100% minus 74 would also give us 26%. And in fact, these 2 events are called complementary. So the probability of an event plus the probability an event doesn't occur are called complementary events. And they always add to 100%. Find the overall probability that someone 18 or older drinks at least 1 cup of coffee per day. Overall probability. So this is the total in the table. Let me just go back for a second. Pull up the table again. We want to go down to the bottom of the table. So now we're looking at, we're looking at the total overall 895 divided by 529. And let me skip ahead. It's on this one. Yeah. So about 59%. And notice this percent falls within the range of the other percents. Remember, the youngest group was 48, the next group was 66, and the third group was 74. So 59 falls kind of in the middle there. Let's see. So these were all called experimental probability. So in other words, we didn't know the likelihood or the probabilities till we actually asked the questions or did a survey. It'll tell you in the problem how to answer it. It'll say, give me a percent, and in that case, the percent will show in the answer, or it'll say, give me a decimal. Sometimes it'll say, give me the fraction. So it depends on the problem. Good question. All right, so now let's talk about theoretical probability. And this is where you know how likely things are to occur. So you don't have to do an experiment. And so, for instance, I've got a handout for you on the deck of cards. So we know if we draw a card from a deck, how likely it is to get different kinds of cards in there. So these are called theoretical probabilities. So the outcome of an event is an outcome of an experiment that's conducted, and the probability of that event is written as capital P parenthesis E. Probabilities go from 0 to 100 or 0 to 1, and the probability of any event is going to be between 0 and 1. And a couple more facts about probabilities. So an event that has a probability of 0 is impossible. It can't happen. A probability of 100% means sure or certain. It must happen. And the theoretical probability is given by this formula. The probability of the event is the number of favorable outcomes divided by all the outcomes. When we list all the outcomes, we're finding the sample space. The number of items in the sample space gives us the denominator. So let's try an example. We roll a single die. Has 6 faces, right? 6 outcomes. And we want to know what's the probability or likelihood we get a 5. So how many outcomes are there in the sample space? 6 possible outcomes. And how many of those are a 5? Just 1. So the probability of rolling a 5 is 1 out of 6. We didn't have to actually roll the die to come up with these probabilities because we know they're equally likely and we know how likely they are to occur. So let's try a couple examples. Suppose you have a bag with 5 blue marbles, 14 red, and 9 green, and you pick 1 marble out of the bag. What's the theoretical probability of picking a blue marble? So first, needing how many marbles are in the bag? Looks like 5 plus 14, 19, looks like 28, and how many of those are blue? 5. So the probability of picking a blue marble is 5 out of the total number of marbles in the bag, 28. What's the probability of picking a green marble? 9 green out of 28. Let's see if I have some more on this one. I think I have a different example. Alicia has a question, that's why I'm waiting. Oops. Yes, you're always going to simplify. I don't think so. I think they're always going to ask you to simplify the fraction, definitely. Okay, we're going to move on now to rolling 2 die. And this again is in the example because some students are not familiar with this one. Let me go down here. If we roll 2 dice, and this little grid here, they show you let's say the first one's the red and the second one's the blue. There are 36 outcomes when we roll 2 die. So 6 outcomes on the first one and 6 on the second one. And in fact, in the material next week we'll go through how to calculate sample spaces. But we want to get the theoretical probability of getting a sum of 5 when we roll 2 fair die. So by the sum we mean, if we look at the face of the 2 die, what do the numbers add up to? So like here, 2 plus 4 is 6. 4 plus 5 is 9. And we want to know the likelihood of getting a sum of 5. Okay, so again, if you look at that little grid I just showed you, if you look across here, here's 5. 1 plus 4 is 5. 2 plus 3 is 5. 3 plus 2 is 5. 4 plus 1 is 5. So it's 4 out of the total of 36. So the probability is, oh, my thing moved over here, shoot. It should say 4 out of 36 or 1 out of 9. Let me see if I can write this in here for you. So 4, whoops. And Alicia, here's one of the times when I simplify, or I reduce the fraction, simplify the fraction. So 4 out of 36 is the same thing as 1, whoops. Hard to do this with your mouse, 1 out of 9. Okay, so this would be the correct answer to put in, not the 4 out of 36, but the 1 over 9. So the probability of an event occurring and the probability of it not occurring, this is something I mentioned before, have to add up to 1. Oh, Alicia, I thought you were typing something, but nothing came up. Okay. No, because remember, probabilities have to go between 0 and 1. So the numerator is always going to be equal to or less than the denominator, because your probability can't be more than 1 or 100%. Good question, though. All right, so let's look at this one. This is what I was talking about before. The probability of an event occurring and the probability of it not occurring have to add up to 1, or the whole sample space probability. So for instance, if there's a 70% chance of rain, there's a 30% chance that it won't rain. And if we know the probability of getting a 5, remember when we talked about the sum of 5 on the dice was 1 out of 9, then the probability of not getting the sum of 5 is going to be, and again my little fraction moved over there, it's going to be 8 over 9. Because the probability of an event plus the probability of the event not occurring has to add up to 1 or 100%. So if this is 1/9, the rest of the sample space probability has to be 8 over 9. And I put a little extra thing there. Let me just erase that. All right, so a couple more examples. This is in your book on page 275. Suppose there's a raffle and there are numbered tickets. One ticket is going to be drawn from a hat and your ticket number is 121. Find the following probabilities of winning, and we're going to show these answers here as a fraction, a decimal, and a percent. So you'll see all there are 3 ways to write the answers. So if there are 200 tickets, what's your chance of winning? So it's going to be what? They're only going to pick 1 ticket, so it's going to be 1 out of 200, which is equal to, and you can do this in your calculator, 0.005, and then to get the percent, multiply the decimal by 100. So it's a 0.5% chance of winning. Now what if I change the scenario and now there are 400 tickets? So your chance of winning is going to be 1 out of 400. Divide to get 0.0025, and then multiply that by 100 to get the percent. So it's a 1/4% chance now. And then let's make it even more interesting and say there's 1,000 tickets sold, and there's only one winning ticket. So what's your chance of winning? 1 out of 1,000, divided to get 0.001, multiplied by 100 to get the percent, which is 0.1%. And you have some homework where they have you do the fraction, the decimal, and the percent. So this is a good review of those answers. Okay, so that's the material for this week. So we're starting the cycle on, it's called what are the chances? So we're going to do the means, and then we did the theoretical and experimental probability. And then next week we'll be doing the standard deviation and also some statistical literacy, a lot of definitions and talking about how data is collected, studies and experiments and things like that. So these 2 weeks leading up to the midterm are all on probability and statistics. All right, any questions? And I hope that both of you saw how I changed due dates. So your things have been extended a bit in certain instances. So take a look at the updated schedule and you'll see those new due dates. And don't forget our midterm's coming up in a little bit more than 2 weeks. So the semester's going quickly now, especially with time that we had off. So hopefully everybody will be able to get back on track. Oh, absolutely. You guys didn't have power. I know a lot of students didn't. So, but I need to get you through these 2 cycles before the midterm. So that's why we had to get everything done now before the midterm's going to be given on, let me check the dates, the 6th, 7th, and 8th of October. And you should get an email this week from the test coordinator about making your appointment for your midterm too. There was a little problem, I think, with the reservation system, so that should be fixed up hopefully today, and then they'll send you an email about making your appointments. Great. Okay, good, Thomas. Okay, Alicia, are you okay now? And you found that handout, right? Remember you were asking me about for the perimeters and areas, right? Good. Okay, guys. All right, have a great week, and then next week, like I said, we'll have the second part of the statistics and probability, and then on to the midterm. All right. Take care, everybody.